Finally, we come to the end, the first part, up to the linear MHD theory. Here's an overview, at least the part that I think is rather important. So we start with go from the different description of a plasma, go from the most precise to the least. So single particle motion, we go to the gyromotion, basically circular motion of a particle perpendicular to the magnetic field line, and along the center of the circular motion we have a guiding center. The guiding center is drift subjected to a drift. If there's an external force, the external force can be electric field, gravity, curvature, stuff like that. So F, that's the most typical one, E cross B drift. This will become QE. So yeah, and then we go to the kinetic. We haven't talked about it. I would just like to mention like the things, the stabilities, the instabilities. For instance, the KBM, ITG, ETG, ITG TM, ETG, MTM. Kinetic ballooning mode, ion temperature gradient mode, trap electron mode, electron temperature gradient mode, microternary mode, and stuff like that. We'll cover in the next part. And the Landau damping and Landau resonance is the textbook kinetic effect that most book will mention. And then here's the part that we're dealing with for the first part of this video series. So the fluid description, we have a cluster of waves that we studied. So for unmagnetized plasma, magnetic field equals 0, we have a plasma oscillation. Basically, the electric field, so there's separation of charge, and then they start to oscillate with no resistance. We're considering no perfect conductive scenario. So of course we didn't consider there's any temperature. And with finite temperature, we have electron plasma wave. See, we consider the basically the pressure gradient, and then ion plasma wave and sound wave. Sound wave doesn't necessarily need to have any plasma. This sound wave happens in the neutral medium as well. For magnetized plasma, we derive the dispersion relations and then get two typical scenarios: K parallel to B, K perpendicular to B. For high frequency scenario, we have left hand, right hand waves, like that, and we have a shear Alfven wave, or we most of the time call it Alfven wave, is a low frequency scenario. For K perpendicular to B, we have ordinary wave, extraordinary wave. One is parallel, another is perpendicular to the electric field. Those are high frequency scenarios. And we have a compressional Alfven wave, or magnetosonic wave, is in the low frequency spectrum. And that's all the waves we studied. And then we go to the MHD, which is consider two different species into one. That become MHD, magnetohydrodynamic. And we divide it into two different scenarios. One is ideal MHD, which is perfectly conductive, and resistive MHD. So for ideal MHD, we study the cylindrical plasma, a cylindrical column of the plasma, and we discuss the Z pinch and theta pinch. And Z pinch is the current going in the Z direction, and theta pinch is the current going in the theta direction. And we discussed about 4 different instabilities: sausage instability, kink instabilities, and really Taylor instability, Kelvin-Helmholtz instability. So those two are the imbalance of a grad P and the J cross P. This is due to the density imbalance, and this is the due to the flow shear. And then we talked about resistive MHD, the magnetic reconnection. Say that there's a magnetic shear, then we'll have a magnetic potential in between. Then if it reconnects, then the extra energy will be emitted in terms of ohmic heating, for instance, and this is what triggered the Turing instability. So that's the whole picture, and there's some concept that we mentioned in the along the class. That adiabatic invariant, there are typical three magnetic moment, longitudinal invariant, and the magnetic flux. And we talk about the equilibrium of phi independent equilibrium on ideal MHD Graf-Shabanov equation, or in other words, it could be, for instance, a torus, and this is the expression. Of course, I cannot get into details. So this is the overview. I will put all the details, all the links to the videos on the description. And Debye shielding, and basically outside the sphere, outside the sphere, with a radius of lambda d, the particle won't feel the electric field exerted by the particle outside of the sphere. And stability study, we talk about those instabilities. Most of the time we use dispersion relations, apply boundary conditions to have dispersion relations to study the stability of it, and also sometimes we use the energy principle to have a physical feeling of that as well. And of course, I suppose there's other ways to study stabilities. Yeah, so that's the overview of part 1 up to linear MHD theory.